So the other part of this section deals with area. So now that we've got some tools to talk about area, let's actually calculate an area between a curve and the x-axis. So let's look at the 16 minus x squared. So that's the parabola that's upside down. And let's look at the interval that goes from 0 to 4. And since we don't have a formula to calculate that area directly, then we're going to use rectangles to approximate what this area is. So we're going to divide our interval up into regions. Let's divide it up into 4 equal regions from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. And we have an option of doing either a left hand or a right hand sum. When we do a left hand sum, we use the left hand of each interval to draw a rectangle. So here's our first interval. So we're going to use the left hand, and we're going to use the y value of our function on the left side of the interval to determine how tall our rectangle is. And then in the next interval, we're going to go to the left side, and the left side of that interval, that's where we're going to touch our curve. And we're going to touch the curve on the left side of the next interval and on the left side of the next interval. So the reason we're going to use rectangles is rectangles are shapes that we know how to get the area for. Area of a rectangle is just length times width. So for this one is a left-hand sum. 1, 2, 3, sorry, can't count. 1, 2, 3, 4. And we can get this y value from plugging these numbers into our function. So this y value is just f of 0. This y value is f of 1. This y value is f of 2. This y value is f of 3. So if we number these rectangles 1, 2, 3, 4, then the area of the first rectangle is given by its height, f of 0, times its width, and each of these rectangles have a width of 1. So if we substitute a 0 into our function, we get 16, and our width is 1. For the second area, for the second rectangle, the height of the rectangle is given by f of 1, and the width is given by 1. So if we put a 1 into our function, 1 squared is 1, so our height is 15 times 1. The area of the second rectangle, the height is given by f of 2. The width is 1. So the area of the third rectangle, plug a 2 in, so we get 12. The width is 1. And the area of the fourth rectangle comes from the height, which is given by f of 3, times the width. So if we put a 3 in, 3 squared is 9, so we get 7 times 1. So we can approximate the area of that by adding these up. So 16 plus 15 plus 12 plus 7. 16 plus 15 plus 12 plus 7. So we get 50 as our sum. Now that is not the exact area, of course, because we have extra area at the tops of these. We have more than enough, so this is also referred to in this case as an upper sum. If our sum exceeds the actual area, that's what we refer to as an upper sum. So let's do this same function over the same interval, and let's do a right-handed sum. So again, our function is 16 minus x squared. So we're going to do this, and we're going to go from 0 to 4 for our interval. We're going to break our interval up into 4 rectangles. we didn't mention this earlier, but the width of the rectangle, we're going to refer to that as delta x. So the width is 1, and n is going to be the number of rectangles, so 4. So if we're going to do a right-handed sum this time, then we're going to use the y value associated with the right side of the interval. So the right side of the first interval is 1, so we're going to use the y value at 1 to determine the height of that rectangle. The next interval goes from 1 to 2, so we're going to use the y value at 2 to determine the height of that one. 3 for the next one, 4 for the last one. Notice when x is 4, y is 0, so our last rectangle has a height of 0. So all of these we're touching on the right side of the interval. Hence, this is a right-handed sum. This is also going to be a lower sum because when we add up our areas, it's going to be lower than the actual area. So this is f of 1, this is f of 2, this is f of 3, and this is f of 4. So if we number these, the area of the first rectangle, the length is given by f of 1, and the width is 1. For the second one, the length is given by f of 2 with a width of 1. The third rectangle has a height of f of 3 and a width of 1. And the next one has a height of f of 4 and a width of 1. So when we put 1 into our function, we got 15. When we put a 2 into our function, we got 12. When we put a 3 into our function, we get 7. And when we put a 4 into our function, we get 0. So our lower sum, our right-hand sum, is just 15 plus 12 plus 7. 15 plus 12 plus 7, which is 34. So that's the lower sum. There's area underneath our curve that is not included in here. So our actual area is more than what we just got. If we could find the area of that red region, that's how much unincluded area. So the actual area is somewhere between 50 and 34. So how would you expect that we could get a better approximation? Might be possible that we could use different shapes. But let's look at what would happen if we included more rectangles. So if we take this same function, f of x is 16 minus x squared from 0 to 4, and instead of breaking it into just 4 intervals, if we broke it up into 8 intervals, let's do a left-handed sum. Then, while we're going to have more rectangles, since our rectangles are not very wide, we're not going to include as much extra space at the top of each one of them. Or if we were doing a right-handed sum, we would not be omitting quite as much. And if we wanted a better approximation, then we would get more rectangles and more rectangles. So if we let the number of rectangles go to infinity, then this amount of extra would get smaller and smaller and smaller until the extra area essentially went to 0. So that would give us the exact area. Of course, who wants to draw an infinite number of rectangles? No one. So we need to see, can we come up with a method that allows us to get a formula for n rectangles, the area for n rectangles, and then once we get that, then take the limit as n goes to infinity. So let's see what we can do. Let's go back and look at the examples we've done. So we calculated, or we said that our delta x in this case is 1. How do we get delta x? So we take the width of our interval, b minus a, where our interval goes from a to b. So 4 minus 0, so our width is 4. And then we divide that into, in this case, 1, 2, 3, 4 equal pieces. That's going to be our n, the number of rectangles. So for ours, 4 minus 0, a width of 4 evenly divided into 4 pieces makes 1. But we need some generic notation so that as our number of rectangles increases, we don't have to redo the problem by hand every single time. So this is our formula to get delta x. So let's look at our intervals. So our interval started at 0 and then it went 1, 2, 3, 4. And we were doing a left-hand sum, so we needed f of 0, f of 1, f of 2, and f of 3. So let's let I be our counter. So when I is 1, that's our first one, and we're doing f of the left, this one. Let's, yeah, this is fine for now. And then when I was 2, we did f of this one. And then when I is 3, we do f of 2. And when I is 4, we do f of 3. So we're going to, since those x's are changing, we're going to denote those x's as x sub I. So we're going to evaluate our function at each of those x's. Our rectangle is our function value. These are our lengths. So our function value at each x sub I times the width, which is delta x. And we need to add all of those together. So we're going to sum that from I equals 1 to, in this case, 4. But other cases, n. So we need a formula for x sub I. The left side of our interval is our starting point. And notice the first time we don't go over a delta x. We just use 0. So we go over no delta x's. So that's our x sub 1. For our x sub 2, we started at 0. And we're plugging a 1 in, so we've gone over 1 delta x. For x sub 3, if we're starting at 0, for our third one, we go over 1, 2 delta x's to get to our x value. And for our last x, starting at 0, we go over 1, 2, 3 delta x's. So generically, x sub I is our left side. Notice this number and I are not the same. This number is actually 1 less than I. So I minus 1 times delta x. That's the formula for x sub I if we're doing a left-hand sum. If we're doing a right-hand sum, then we're using 1, 2, 3, and 4 as our x values. x1 is 1, x sub 2 is 2, x sub 3 is 3, and x sub 4 is 4. So starting at 0, to get to 1, we've gone over 1 delta x. Starting at 0 to get to 2, we've gone over 1, 2 delta x's. To get to 3, we've gone over 3 delta x's, and to get to 4, we go over 4 delta x's. So generically, sometimes they'll use a capital x here. We start at the left side, a, and this time the number of delta x's and the subscript match. So I times delta x. Notice that formula is a little simpler. So often, as we let the number of rectangles go to infinity, we use this formula because it's easier to evaluate. And if we do the left-hand sum or the right-hand sum, as we get more and more rectangles, we're going to get a better and better approximation. And as n goes to infinity, the left and right-hand sum are going to approach each other. So let's summarize what we need. So the area of our rectangles is our function at each x value needed times delta x. We're going to sum those from 1 to n, where delta x is b minus a over n, where x sub I for a left-hand sum is a plus I minus 1 times delta x, and for a right-hand sum, it's a plus I times delta x. So let's evaluate a sum using these formulas. So let's just do the one that we've already been looking at. Let's do f of x is 16 minus x squared. And our interval is going to go from 0 to 4. And we want to look at the area underneath there. So we're not going to necessarily break this into any particular number of rectangles. We're going to leave it in terms of n. So delta x is b minus a, and we're going to do it again generically. So our delta x is 4 over n. So let's do a right-hand sum. So x sub I is a plus I delta x. So 0 plus I times 4 over n. So our x sub I, we could call that 4I over n. Now keep in mind that I is not the square root of -1. That I is just a counter for our sum, because the area of one rectangle is f of x sub I times delta x, and we're adding those where we let I start at 1 and go to n. So for us, we need to substitute in our x sub I into our function. So 4I over n goes into our function, and our delta x is 4 over n. For each function and for each interval, we have to determine what is our x sub I and what is our delta x, so we'll know what to plug into our function. Now, we need to evaluate our function at 4I over n. We need an expression for that. So if we substitute 4I over n into our function, we get 16 minus 4I over n squared. So 16 minus 4 squared is 16, I squared over n squared. So this is what we get for the function part. 16 minus 16 I squared over n squared. And we're going to multiply that times 4 over n. So let's distribute that. 16 times 4 over n, that's 64 over n. And 16I squared times 4, that's 64I squared over n squared times n, that's n cubed. And we want to evaluate that sum from 1 to n. So now we have formulas for evaluating these sums. We have two terms, so we break this up. The sum of 64 over n minus the sum of 64I squared over n cubed. Notice our variable for our summation is I. For this first summation, there's not an I on the inside, so that whole thing is a constant. So remember how we do the sum of a constant. We take the number on top times our constant. N is specific to how many rectangles we're going to have. So once you tell me that, that's not changing as far as our summation. Now for the next term, we do have a variable. I is our variable for the counter for our summation. So we're going to leave the variable part on the inside, and we're going to put the part that's not an I on the outside. So that first term, the n's cancel, and we get 64. For the next one, we need to evaluate the sum of I squared from 1 to n. And remember, there's a formula for that. Sum I squared, it's n times n plus 1 times 2n plus 1 over 6. So this n will cancel one of these. 2 goes into 6. 2 goes into 64. And now we need to just do some algebra and simplify this farther. So let's put our 32 over 3 out front, along with our n squared. And then let's multiply that together. N times 2n is 2n squared. N times 1 is n. 1 times 2n. And 1 times 1. So when we full that out, we get 2n squared plus 3n plus 1. So now we can make the parentheses go away by distributing, taking our 32 over 3n squared and multiplying it times whatever we got there. So when we multiply these together, the n squared on bottom and that n squared cancel, leaving us 32 times 2 over 3. When we multiply those together, a negative times a positive is negative. This n will cancel one of those n's out, so we're going to be left with one n on bottom. That 3 and that 3 cancel, so that leaves us 32 over n. When we multiply those together, 1 times anything is itself. So this is a formula for the area in terms of n. You tell us how many rectangles we have, then that'll be the area we did for the right-hand sum. When we calculated x of I, we use the formula for the right hand. So we could check that to see if that formula works. We calculated the area earlier of the right-hand sum using 4 rectangles. So if we put in a 4, 32 over 4 is 8. And here, if we put in a 4, 4 squared is 16, times 3 is 48. So we can reduce this. 16 goes into 32 2 times, 16 goes into 48 3 times. This and this both have a common denominator. So we have it 64 minus 8 is 56. Notice this is a minus 64 and that's a minus 2. So minus 64 minus 2 is minus 66 over 3. 66 over 3 is 22. So we get 34 for that. So that's the area when we have 4 rectangles and we're doing a right-handed sum. So if we go back to where we did the right-handed sum, notice we got an area of 34. Now you might say, well, that's a lot of work to get that area when we could have just drawn the rectangles, and that's exactly right. But what if we wanted to increase this to 8 rectangles or 16 rectangles? We wouldn't want to have to draw each one of those rectangles. So now we can put in, let's say, a 16. And we can find out what the right-hand sum would be with 16 rectangles. So that would be 64 minus 64 thirds minus 32 over 16 minus 32 over 3 times 16 squared. And instead of getting this as a fraction, I'm just going to get a decimal approximate just to save time. So we have 64 minus the result of 64 thirds minus 2 minus the result of doing 32 over 3 times 16 squared. And that's about 40.625. So I say about when that gave us a terminating decimal, so that's actually the exact area for 16 right-handed rectangles. So if we wanted to get a better approximation, we could let the number of rectangles be 100. If we put 100 into our formula, we have 64 minus 64 over 3 minus 32 over 100 minus 32 over 3 times 100 squared. So each time we're just going back and into our formula that tells us area. When you tell us the number of rectangles, we're putting in how many rectangles we want to use for our approximation. So let's do that. 64 minus 64 thirds minus 32 over 100 minus 32 over 3 times 100 squared. And we get about 42.3456. So that's the area if we were to break it up into 100 rectangles. So we could do 1,000 and 10,000. So how would we get the exact area? How many rectangles would it take? And so we would need to let the number of rectangles go to infinity. So we can take our formula for the number of rectangles. Oops, that's not what we wanted to copy. So our formula for the area was so if that's the area for a finite number of rectangles, the limit as n goes to infinity of 64 minus 64 thirds minus 32 over n minus 32 over 3n squared, and whatever we get, that's our actual area. So the limit of a constant is that constant. And remember, if we let the denominator go to infinity, that term goes to 0. So the last two terms both go to 0 as n gets really, really big. So our actual area is 64 minus 64 thirds. That's the exact area. Now let's get a common denominator. So let's multiply top and bottom by 3. So 192 minus 64 over 3, because 3 times 64 was 192. If we subtract 64, we get 128 over 3. That's the exact area. If you wanted that as a mixed number, 3 goes into 12 4 times. 3 goes into 8 twice with 2 left over. So at 42 2/3, which is 42.6 repeating. We did 128. 128 over 3. 42.6 repeating. So when we put in 100 for the number of rectangles, that was getting us very close. So this is how we can get the exact area under any curve.